Hello folks, so let's continue on the theorems on circles. Today we'll look at the properties of a cyclic quadrilateral, right? If you remember when we looked at the properties of a circle, we also touched upon inscribed and circumscribed polygons, correct? A polygon is a closed figure with three or more sides, and an inscribed polygon is one where all the vertices of this polygon lie on a circle. So here in figure 1, we have a quadrilateral whose vertices lie on the same circle. All the vertices lie on the same circle. And out here we have 1, 2, 3, 4, 5, 6, 7. This is a septagon whose vertices lie on a circle. So these two are called inscribed polygons. Now a triangle is also a polygon, right? So when we have a triangle that's inscribed inside a circle, then this circle becomes the triangle's circumcircle, right guys? Fantastic. Just like you can have a polygon inside a circle, you could have the other way around too, where a circle is sitting inside a polygon. Okay, in such a case, you call it a circumscribed polygon. So here, each side of the polygon becomes a tangent to this circle. What's a tangent, folks? A tangent is a line that touches the circle only at one point, right? At one point, and we call this the point of contact. So in today's video, we'll quickly look at what are the properties of inscribed polygons, and that too a quadrilateral only. So a quadrilateral that is inscribed in a circle is called a cyclic quadrilateral, right? Something like the figure that you see here and the second one. But what about this quadrilateral? The vertices are A, B, O, and D. It's a four-sided figure. It is indeed a closed figure, so it's a polygon. But is this a cyclic quadrilateral? Not necessarily, because one vertex, which is O, does not lie on the circumference of the circle, but it lies inside the circle. So this is not a cyclic quadrilateral, correct? You can also remember the fact that this particular quadrilateral is called a concave polygon. Right, guys? Even if one angle of a polygon is a reflex angle, then we call such a polygon as concave polygon or concave quadrilateral. Fine. And moving on, we have another example here. Let's say this is P, Q, O, and S. Another quadrilateral, but this is also not a cyclic quadrilateral. Why I'm showing even non-cyclic quadrilateral is sometimes when you're working on a lot of sums, you see a quadrilateral and you forget the fact that there is one vertex which is not on the circumference. Okay, guys, so just bear that in mind when you're working with cyclic quadrilaterals. Fantastic. So now let's jump into the properties directly. We have looked at one property, which is the one about opposite angles of a cyclic quadrilateral in the previous video. But let's try and have a generic proof for that. So here's a circle with center O. Here's a quadrilateral with vertices A, B, C, and D. Okay. And let's find out what is the relation between angle A and angle C, which are the opposite angles, and what is the relation between angle B and angle D. Okay. So here, for the first one, let's try and join OB and OD, right? Now, what you will see is that BD is the minor arc, okay? BD, arc BD is the minor arc. And this way around, arc BD is the major arc. So, if angle A were X, let angle A be X, then what do you think is the central angle of the arc, minor arc BD, which is angle BOD, correct? So we know that angle subtended by an arc at the center is twice the angle subtended by the same arc anywhere else. So this angle becomes 2x. Right, guys? Now, what about the reflex angle BOD, or the central angle of the major arc, BD? This becomes a 360 minus 2x because angle about a point is 360 degrees. Right, guys? Now, if we look at angle C, what could angle C be? Okay, now this is going to be half of the angle subtended by the major arc, right? This is half of the angle subtended by the major arc, which will be half of 360 minus 2x, which in turn is a 180 minus x. Are we clear with this, folks? So all we did was we started with one angle, which is angle A, and we looked at the major arc and the minor arc and their central angles, and we applied one fact, which is the angle subtended by an arc at the center is twice the angle subtended by the same arc anywhere else. So from this, we now know that this angle is a 180 minus x. Okay, so if you look at angle A plus angle C, this will give you 180 degrees. In other words, the opposite angles of a cyclic quadrilateral are supplementary. Okay, this is a very important theorem or outcome that you would use, pretty much everywhere. When it comes to circle sums, you'll see this is one thing that comes very, very handy. Okay, opposite angles of a cyclic quadrilateral are supplementary. Okay, folks, so shall we move on? We'll definitely have another video where we will apply these outcomes in various numerical. Okay. Now let's look at another property of a cyclic quadrilateral, which is, let's find out what happens to an external angle or the external angles. Okay, so let's start with one. External angle of a cyclic quadrilateral. Now bear in mind, for any polygon, there are two ways in which you can draw the external angle. So let's have a circle with center O. Here, if we have a cyclic quadrilateral as shown, then if I start extending one of the sides, let's say I have extended the side BC with this line, okay? So DCE is the external angle, right? One external angle. Now, if I continue in an anti-clockwise direction, okay, then I will have another external angle here, right? And if I continue on the same thing, I get 4 external angles. But bear in mind, this is just one way. Another way of drawing the external angles is we take the same quadrilateral ABCD. This time we traverse, oops, hang in there. This time we are going to traverse the clockwise path. So this is one exterior angle. There's a second, third, and fourth. Okay. What you should not do is, start traversing anti-clockwise and then suddenly for one of the angles change the direction. So ideally, if you start drawing the exterior angle in one direction, please follow the same. Okay, cool. So let's pick this cyclic quadrilateral. Okay, let's call it PQRS. Let's draw the external angles. Here we go. So now let's say angle P, okay, angle P is x degrees. Okay, this is x. What do you know about angle R, folks? We know that angle R is supplementary to angle P because angle P and angle R are opposite angles. And we just now proved the fact that these two add up to 180. So if this is x, this is going to be 180 minus x degrees, correct? Now, look at this exterior angle SRT. Angle SRT is an exterior angle, okay? And not only that, we have QRT being a straight line. So obviously these two angles add up to 180, which is SRQ, this angle, and the angle next to it add up to 180 because they form a linear pair. Am I right? So this and this angle form a linear pair. Therefore, you could say that this angle SRT is actually a 180 minus 180 minus x, which is a plus x. Right, guys? So we started off with one angle and we figured that the exterior angle that's opposite to it is one and the same. Therefore, we can say that an exterior angle of a cyclic quadrilateral is equal to its interior opposite angle. You just have to be careful in picking that angle which is, opposite to this exterior angle. Or another way to look at it is pick the adjacent angle and whichever is opposite to that, it's going to be equal to the measure of that angle. It's interior opposite angle. So we've looked at two important properties. Opposite angles of the cyclic quadrilateral are equal, and the fact that the exterior angle of a cyclic quadrilateral is equal to its interior opposite angle. Okay, guys, we will try and apply this in a few sums in the next video.